Hey guys, Miss Thomas speaking. This is the video for Algebra 2B Unit 5 Asynchronous session. I'm going to focus on Lesson 22, Introductory Statistics. Now the reason I've chosen to focus on this lesson is that it introduces quite a bit of vocabulary. So our goal today is going to be to learn these vocabulary words and then practice applying them in context. So for the sake of these vocabulary words, in order to give you some examples as we go, let's just pretend that we are doing a study on all of the students in this math class. Again, pretend we're doing a study on all of the students in this math class. So our first definition, data. This is a term I'm sure you're familiar with. To keep it simple, we'll say that a data are just pieces of information. Now those can be quantitative, meaning numbers, or qualitative, meaning something other than numbers. It's some sort of characteristic. So for example, qualitative data might include the day of the week, someone's eye color, things like that, right? So they are qualities about the person or individual that we're studying, qualities, whereas a quantitative piece of data would be something involving a number or a quantity. So if we're doing a study on all the students in this math class, one piece of data might be the age of all of the students in this math class. That could be a data set. And of course, that would be a quantitative data set. Next, an individual, just a single object, some sort of noun. So depending on what the study is, the individual could be a person, an animal, it could be a country. Just think of an individual as a noun, and it's the subject that we're studying. So in our example of our study of students in this math class, an individual would just be one of the particular students in this class. The population is the entire group of individuals about whom you collect data. So in this case, our entire group of individuals would just be all of the students in this math class. So if you're having trouble figuring out who the population is, it might be easier to start by thinking about who an individual in a study is, and then you would know that to figure out the population, well, it would just be the complete group of those individuals. A sample is a selection of individuals from the population. So if our whole population is all of the students in this math class, a sample could just be all of the female students in this math class. Okay, and that was a specific sample with females, but it could be a random sample. It could be a sample based on any number of criteria, okay? But again, a sample is just a selection of individuals, meaning not the entire population. So a sample is a piece of the population. A survey is a study that asks questions of a sample. And I'm sure we've all heard the term survey before and you're pretty familiar with a survey. The key here is that a survey is drawing information from a sample. This is different than a census, which is a study that asks questions that draws information from a population. So let's look at an example of a survey and a census. So again, our study on students in this math class, a survey would be if someone decided to ask questions of just the female students in the class, this would be a survey. A census would be questions asked of all of the students in this math class. Now notice that most of the time in day-to-day living, especially on the internet, we'll hear about survey statistics. The reason we hear about surveys much more often than a census is of course because they're much easier to do. Right? So imagine that you're trying to gather information about all men aged 25 to 40 or all people in the United States or all pet owners or something like that. It's going to be difficult to contact and get information from every single individual from a population. So instead, a survey takes a sample of the population and asks questions or does some sort of measurements with them. A census, on the other hand, probably the most relevant example, you might be familiar with the United States government census, where once every 10 years they will ask all of us to fill out information about our household, how many people are living there, ages, income, things like that, right? And the reason this is only done once every 10 years is that, again, it's difficult it's timely, and it's expensive. So in most cases, we'll be talking about a survey, but if the study is just on students in this math class, that's a pretty small population that we're talking about, and it would be much easier to conduct a census, right, when we have such a small population. So again, survey corresponds to a sample, a census corresponds to a population. Now we're not done yet, so if you need to, go ahead and pause the video now, review and make sure you understand the vocabulary words I've covered so far. We have a couple more we're going to go through, and then we'll get into some practice with identifying and interpreting these vocabulary words. So continuing, assuming that we're doing a study on the students in this math class. An explanatory variable is a suspected cause of a relationship. It's kind of like when we talk about x being an independent variable, the explanatory variable is similar but not the same, which is why I didn't write it down. So for example, as the teacher, I might say to myself, it seems like all the top performing students are a little bit older. I think age might explain why some students get higher grades. So age is my explanatory variable. And again, it's just something I'm suspecting. Now, on the other hand, we have our response variable, the outcome being measured. So if I look back to this example, what's the outcome I'm measuring? What's the thing that I'm trying to explain? Well, I said age explains why certain students are getting those higher grades, right? So that's my response variable. Response variable, outcome being measured. In this example, it would be the student grades. That's the outcome I'm measuring. Next, a random sample, and I mentioned this briefly on the last slide. I've included the formal definition of a random sample, and I think it's important that we just read through it to get an idea, and then we'll talk about it more informally. So a random sample is a group of n individuals. N in this case is just some unspecified number of individuals, some number of individuals that are selected from a population in such a way that any group of n individuals has the same probability of being selected as the group that is actually selected. So to make this a little more clear, let's plug in a number. So let's say, for example, we want to sample 10 people. Okay, say we want to sample 10 people out of, I don't know, out of 100. So I have a population of 100, and I've decided that I'm going to take a sample of 10. So in order for my sample to be truly random, I'm saying that I've selected 10 people at random, but it would have been equally likely that any group of 10 people from that population would have been selected. Let's say that one more time. Assuming I had a population of 100 and I decided to pick a random sample of 10, my sample is truly random if the 10 individuals that I chose were equally likely to have been picked as any group of 10 individuals from that same population. Okay, so in other words, I think we know what random means, right? Equally likely of having picked any group of 10 with any 10 members in it, okay? Again, I know this definition is a little bit formal. Try not to overthink it. It's the name of the term is not misleading. Random, so equally likely, no bias, and sample, a piece of the population. So for example, if we're talking about students in this math class and I decided I wanted to randomly sample 5 students, one way that I could get this random sample is that I could write all the students' name on equally sized slips of paper, fold them in half, and then draw 5 of them, right? And maybe I've mixed them around too, and I draw 5 of them. That group of 5 pieces of paper with the 5 student names on it that I drew were just as likely to have been picked. That group of 5 were just as likely to have been picked as any group of 5 that I could have come up with from that population. A lurking variable. This is a variable that is not an explanatory variable, but might affect the response variable. And it's important because it can lead to false conclusions, it can lead to bias, or in other words, it is a bias that we're not noticing. So for example, earlier I said that, Pretend I've noticed that a certain group of students is doing better than the rest, and they all happen to be a little bit older. So I've said that, you know what, maybe age explains why they're getting higher grades. But there could be lurking variables that I'm not taking into consideration. For example, maybe it turns out that I've assigned all of these older students the front row of seats, and so they're more likely to pay attention because they're right in front of me, they can hear me well, they can see the board, things like that, right? Or maybe I just favor them. Maybe these older kids, for whatever reason, I've picked as my favorite and I treat them, I grade them easier or something like that. Maybe they're older, they have jobs, and they can afford tutors for the class. So it's really that they get tutoring because they can afford it and not because they're older, right? So these could all be other things that could explain why it seems like age is leading to higher grades, but really it's this other thing that we didn't take into account. And this is a really important um, concept that hopefully after this class, as you start reading about things, whether online or in a paper or something like that, your eyes start searching for lurking variables when you hear about kind of suspicious sounding statistics. So a parameter, a measure of a specific characteristic of a population. And let's also at the same time look at statistic, which is a measure of a specific characteristic of a sample. So the only difference is that a statistic comes from a sample, a parameter comes from a population. So S for statistic, S for sample, P for parameter, P for population. Okay, so for example, a parameter for our study on the students in this math class could be the average height of all students in the class, whereas a statistic might be the average height of a certain sample of students in the class, right? So let's say we have a class of 30 students. If I had measured 10 of 30 students, that would be this average height that I measured would be a statistic. If I measured all 30 students, then this average height that I came up with would be a parameter. So notice that in these two examples, I'm using the same characteristic, right? I'm measuring the same thing. The difference is whether I drew that, the average height, whether I drew it from the entire population or just from a sample of the population, okay? So again, P for parameter, P for population, S for statistic, S for sample. And a treatment. A treatment is a combination of factor levels, and a factor is an explanatory variable that is manipulated by the experimenter. So I know that definition is a little confusing, but let me give you an example. So going back to figuring out things about students' grades. Let's say I think to myself, I want to figure out what I can do for the students in my class to help improve their grades. So say I split them all into groups, and one group I give them extra homework every night. And another group I put in a study group and I tell them that they have to study together 1 hour every day. And another group I put together, and it's the same thing, I put them in a study group, but the teacher, me, I'm going to study with them. So I have one group of students with extra homework, I have a group of students in a study group, and then I have a group of students in a study group with a teacher. Each one of these things that I'm doing are different treatments, okay? There are different treatments that I'm giving each group to kind of figure out what might improve student grades. So that's it for vocabulary. At this point, I'm going to take you through some examples of different ways you might have to interpret, apply the vocabulary concepts from this lesson. So it's not going to be a case of plug and chug where we can kind of do something once and then you know how to do all the problems of that kind. Each example is going to be different. It's going to require you to apply your definitions and pay close attention to context, but with a little practice, I think you'll get through this lesson just fine. But you really have to keep your vocabulary fresh in your head. I would keep your definitions on hand as you go through this lesson for easy reference. And by the way, all of the definitions I provided will be available in lesson 22 in the research section of the lesson. Okay, so let's look at some examples. Let's say a researcher is conducting a worldwide study of the bone density of women with osteoporosis. The set of all women in the world with osteoporosis is the blank for the study. So say it's a multiple choice question and it gives you these options. The first thing I would do is pull up the definitions for each one. So the question is, the set of all women in the world with osteoporosis, what is that representing in this study? Well, right away, I can eliminate data because the set of all women in the world with osteoporosis, that's not really data, that's a group of people, right? It's a group of individuals. And so it's not a statistic either. And it's not a parameter, it's not a measurement of something, right? What we're talking about is a group of individuals, this group of women that have osteoporosis. So in this case, the set of all women in the world with osteoporosis is representing the population of this study. Now, if they changed the question slightly and said that the research is conducting a worldwide study, notice it's a worldwide study, of the bone density of women with osteoporosis. And what if instead of the set of all women in the world, it said all women in the US? Well, that would have been a sample because it's a piece of the population. The study is worldwide, it's for all women in the world with osteoporosis. So if we just had a selection of all the women in the US with osteoporosis, that would have been a sample. Let's move forward. A scientist is studying the height of adult penguins that live in Antarctica. What is the population for this study? So looking at population again, what's the definition? It's the entire group of individuals about whom you collect data. So who are we collecting data about? And notice it's kind of a who question, right? So it doesn't include, they're studying the height, but that's not, a height is not part of an individual, right? So who are the individuals we're studying? We're studying adult penguins that live in Antarctica. And it's important that we specify that they are adults, that they are penguins, and they specified where they're living, right? So if this was a multiple choice question, if it said penguins that live in Antarctica or adult penguins, those would have been incorrect. It's important to include, if the study specifies things like adults or where they live, etc., it's important to specify all of those things when you're identifying the population. So this population, the set of adult penguins that live in Antarctica. So here's another example, and as you can tell, this one is straight from your workbook. And it asks what situation describes a parameter. Remember that a parameter, remember that a parameter, this is a characteristic taken from a population, right? So we're looking for a characteristic that is drawn from information that we get from a complete population and not a sample. So anytime that we see something talking about like part of the population, we'll know that it's not, that would be a statistic, not a parameter. So let's take a look. So Felicia pays an average of $145 a month for electricity. She wants to know how her energy usage compares to all 100 homes in her subdivision. So she gathers data from 5 of her neighbors and compares payments. Well, if there are 100 homes in her subdivision, and she wants to compare herself with them, she would need to, for this to be a parameter, she would need to compare herself with all 100 homes, but she compared herself with only 5, so this is a statistic. Next, Felicia has been living in her home for 5 years. She collects all of the electricity bills that she paid in the last 24 months and finds her average electricity payment is $145. So notice that this is a different scenario. Don't always expect it to be like 4 scenarios with one little thing tweaked. She's doing something completely different here. So in the last example, she was comparing herself with other homes. In this one, she just wants to figure out her own average. So she collected bills from the last 24 months, but she's lived in her home for 5 years. So she did not, when she found this average came from data of the last 24 months, not all 5 years. This is also a statistic. Next. So now she gathers energy usage and billing information from 10 of the homes in her 100 home subdivision and finds that the average energy bill for the subdivision in the past 12 months was $145. So again, because she took information from 10 of 100 homes, this is not a parameter. So finally, as I kind of gave away earlier, this is going to be the correct one, and let's read why. So she collects all of the electricity bills that she has paid since buying her home, and she found her average payment. So keyword, she collected all of the bills that she had paid since buying her home. So since all of her bills were included, she found the average based on the complete in this case, each bill would be an individual, right? So each bill she paid would be the individual, and then added together, it would be a population of bills. We could think of it that way. So since she included each and every one in her calculation, this is a parameter. Next, a virologist is studying the effects of a chemical solution concentration and volumes on certain viruses. Virus specimens are given volume A, B, or C of the solution each day, and that solution, the solution given contains either a 20% or 33% dissolved chemical solution. How many treatments are used in this experiment? So remember that a treatment is a combination of factor levels, and a factor is the explanatory variable manipulated by the experimenter. So hold on. A treatment is a combination of factors. A factor is the explanatory variable manipulated by the experimenter. Let's start here. So what are these things being manipulated by the experimenter? Well, it's said that this person is studying the effects of chemical solution concentrations and volumes, right? So percent concentration and volume. These are the explanatory variables. This virologist thinks that depending on the concentration and the volume, it's going to change the way the virus responds. So these are our explanatory variables manipulated by the experimenter. These are our factors, concentration and volume. So treatment is the combination of factor levels. So this virologist is varying the volume and varying the concentration. So we have 3 different volumes that we're talking about, right? A, B, and C. And we have 2 different concentrations, 20% or 33%. So to figure out the number of treatments, we multiply together, and we find that there are 6 treatments total. This would have worked if there were additional considerations as well. So for example, maybe they also vary exposure time, right? So maybe in some cases, the timing or like the light exposure, some other exposure factor, right? And let's say there are 4 different ways that they can manipulate this exposure. So now I've added additional treatments, but to figure out the total, I would still just multiply. 2 times 3 is 6, 3 times 4 is 24, so this would have been 24 total treatments, okay? All right, let's move on to the next example. The owner of a new music store reviews all payment records and finds that since the store opened 8 months ago, 65% of the store's income has been generated from sheet music. The owner decides to run a sale on sheet music because that is the most popular customer purchase. This situation describes a what? A statistic or a parameter? So this 65% of the store's income has been generated from sheet music. Is that a statistic or a parameter? Well, how was it determined? The owner reviewed all payment records since the store opened 8 months ago. So this is a parameter. If the store owner had monitored all payment records in the last 3 months or something like that, then this would have been a statistic, right? Because it would have been less, statistic, I'll abbreviate. It would have been less than all. So remember, parameter goes with population, and it's all the individuals. Statistic goes with sample, right? And it's just a selection. So S for statistic, S for sample, X for selection of individuals. All right, next example. A meteorologist conducts an observational study in which he measures the hourly temperature of a nearby lake every day for 100 consecutive days. What's the data collected in this observational study? Okay, so we want to know what's the total body of data that we're collecting. So the key here is making sure that you give a complete answer. I have a feeling that most of us could glance at this and figure out at least a partially correct answer, but we want the whole thing. So the meteorologist conducts an observational study in which he measures the hourly temperature of a nearby lake every day for 100 consecutive days. Our data, pieces of information, is the set of all temperatures recording during the study. So every temperature reading for every hour for 100 days all add up to be our complete data set for the study. Simon conducts an experiment to determine which major battery brand produces longer lasting batteries. He purchases a set of brand A batteries and brand B batteries from his local hardware store. So he loads 4 brand A batteries into his flashlight and he loads 4 brand B batteries into his radio. He turns on both devices at the same time and waits to see which shuts off first. Did Simon conduct a well-designed experiment? Why or why not? You'll see a lot of questions asking you this. Is it a well-designed experiment? In other words, is there some sort of inherent bias that is not accounted for? Is there something here that's uneven, unfair? Is there a lurking variable? Is there bias? Okay. So in this case, let's take a look. Let's make sure everything matches up with his experiment. So he purchased a set of brand A and brand B batteries. So they're both new, right? So that's good. He loads 4 brand A into his flashlight, 4 brand B into his radio. So he used 4 each time. But then the devices, in one is a flashlight and one is a radio. So I've got 2 different brands in 2 different devices. And remember, the thing that I'm testing are the brands, brand A versus brand B. But I can't fairly test them if they're not in the same device, right? Because a radio might take more power than a flashlight or vice versa. So since the devices are not the same, this is not a well-designed experiment. He created a lurking variable, which is that the life of the device, the amount of energy the device uses, might be different, okay? Now, again, you'll see a lot of questions about well-designed experiments as you go through your workbook and checkpoint, etc. I encourage you to do something like what I've done here, where you just kind of look at each consideration and figure out if it was done in a fair and even way. And I will leave it at that because I don't want to overcomplicate it. But, just read carefully, take notes, take your time, read it twice, right? And I'm sure you'll be fine with these. Now, this will be our last example. This is another problem type that you'll see in the lesson. So let's say Adrian is a data analyst for a music subscription service, and he wants to know how many of the site's 1 million subscribers stream music for at least 20 hours each month. So he analyzes the data of 500 subscribers, and he finds that 25% of them stream music for at least 20 hours a month. So he concludes that 300,000 of the network subscribers stream music for at least 20 hours each month. Is his estimate reasonable? Why or why not? Okay, I know this is a huge question, but if we boil it down, it's pretty simple. So really, we just have this guy, Adrian, who wants to know something, right? And he wants to know about the subscribers streaming music for at least 20 hours a month. Important. He analyzes the data of 500 random subscribers, right? And it's important that there are 1 million total. So he's analyzing 500 random subscribers of 1 million total. 25% of the 500 stream music for at least 20 hours each month. So based on that, he figures that 300,000 of the total 1 million subscribers are streaming. So what did he do? Well, he said, okay, if 25% of my 500 people are streaming that much each month, then I bet 25% of my total, or my 1 million, are probably streaming as well, right? So this is all he did. He took a sample of 500 people from the population of 1 million. He figured out how many of them were doing a certain behavior. It turned out to be 25%. So then he made a reasonable guess that if 25% of those random people were doing it, then probably 25% of everyone is doing it. Now, we need to check out and see if his numbers make sense. He concluded that 300,000 people are probably doing the same thing. So our question is 300,000 25% of a million? Or another way to say it, what percentage of 1 million is 300,000? Well, 300,000 out of 1 million is 30%. If you did this division, you would get 0.3, which is 30%. So he did not do this correctly, because why would you assume, again, if it was 25% of your sample, then how would you get to 30% in your population? That doesn't make sense, right? So this is not a good conclusion. What should he have concluded? He should have concluded, he should have figured out 25% of the total, which would be 250,000 people. And so here it's left to us to kind of guess if he meant to do 25% and accidentally came up with the wrong number, or if he really did calculate that doesn't matter. The point is that a reasonable guess would have been 25% of the total, which is 250,000. That is not what he concluded. So his estimate is not reasonable. And now we have to answer the rest. So yes or no, which we've said no, he did not use it correctly. Adrian used the statistic or parameter established from his research to correctly, incorrectly estimate the given statistic parameter. So we know he did it incorrectly, first of all. So I can circle that one. So this thing that he used to make a generalization, this 25% of the 500 people, is this a statistic or a parameter? It's a statistic, because he got it from a sample. He got it from not the complete population. He got it from a selection of the population. So no, Adrian used the statistic established from his research to incorrectly estimate the parameter. So he is estimating this estimate of 250,000 people out of the million doing this thing is a parameter. So we use the statistic here, drawn from information from part of the population, to make a guess, to make an educated guess about what the actual parameter is for the entire population. Okay, so that's it for our examples today. I hope this gave you a pretty good understanding of the vocabulary that you'll need to be successful in Lesson 22 and in Unit 5 in general. You guys have a great day, and I will catch you next week for Unit 6.